Hey guys, this is Eddie the Magic Monk. Welcome to another math tutorial. In this lesson, we're going to show you guys how to derive the equations of motion, which are used a lot in physics to work out problems where the acceleration is constant. So another word for these equations is kinematics equations. So what are the equations? Let's write them out first. So these are the equations, and these are the meaning of each symbol with their units in brackets. So t is equal to time, u is equal to the initial velocity, which means when time is equal to 0 what the velocity is. V is equal to the final velocity, that just means at time is equal to whatever seconds what the velocity is, and then s is displacement, and a equals acceleration, and acceleration obviously in the units meters per second squared, right? So this notation means the same thing as meters per second squared. Alright, meters per second squared. So in order to figure out where these equations come from, you have to be able to understand integration and differentiation. So if you have never heard of it before, I can still explain a little bit in this tutorial, but you really have to go through a lot of tutorials on integration, probably on my channel or in other places, to fully understand what's going on. So basically you have the displacement is equal to s, so s equals displacement, alright. And you got the velocity. The velocity is equal to the rate of change of displacement over time. Alright, so v equals change in displacement over change in time. And then you have the acceleration is equal to the rate of change of velocity over time, so dv over dt. Right, so if we want to go backwards, right, so that's differentiation. Going down this ladder is differentiation. So if we want to go backwards and we want to go up this ladder, then we do what's called integration, and we reverse the process of differentiation. So we write it like this, right? The integral of the velocity is equal to the integral of a with respect to time, and the displacement is equal to the integral of velocity with respect to time. So let's start with this equation here. V is equal to the integral of acceleration with respect to time. Now, because in all of our equations we can only take on a constant acceleration. So what that means is acceleration does not change. Acceleration is constant. What that means is does not change. So in our situation, whatever it is, for example, a falling object has the same acceleration the whole time, right? Negative 9.8 meters per second squared for a falling object, right? Because acceleration due to gravity is always the same. So because acceleration is a constant, when you integrate a constant, you just get a, whatever the constant is, times the variable, which is t, plus another constant c. Right, so once we have this equation, if you guys remember, we have a symbol that we use for initial velocity, which is u. Now, when time is equal to 0, v is equal to a times 0 plus c. A times 0 becomes 0, so v is equal to c. Now, if you guys remember, the symbol u is used to represent the velocity when time is equal to 0. So therefore, c is equal to u. So u is equal to v when time is equal to 0, which means u is equal to c. And in this case, I can represent the symbol c with the letter u, so v is equal to at plus u, and that is my first equation. So I've now proved this equation, v equals u plus at. Right. So now that we've done the first equation, let's try and develop the second equation. So we got the displacement is equal to the integral of v with respect to time. And if we try to integrate this equation here, integral of at plus u with respect to time, and if we follow the rules for integration, we will get at squared over 2 plus ut, because u is a constant, plus c. And then we will see that our object, let's assume that the object starts at the origin. So assume object starts at origin. So what that means is when t is equal to 0, the displacement is equal to 0. So if we substitute these two values into the equation, into this equation, the displacement is equal to 0 equals a times 0 squared over 2 plus u times 0 plus c. Anything times 0 is equal to 0, so c is equal to 0. So therefore I can say c is equal to 0 and the displacement is equal to half at squared plus ut, which is our second equation proven. Right, second equation proven. Now let's try to prove the third equation. So the third equation, what we're going to do is, firstly, from the second equation, right now all we have to do is some simple rearrangement and factorization. So let's factorize it. So let's take out the common factor t. So s is equal to s is equal to let's take out t. So it's half a t plus u. Right, so I factorized the t out and put it at the front. So then what I'm going to do is I am going to take out the half as well. So it's going to be half t times at plus 2u. Right, so obviously half t times at is going to give me the original half at squared, and then half t times 2u is going to give me ut, right, because half times 2 is 1. So now what I'm going to do is I'm going to rewrite the inside. I'm going to separate the two u's and I'm going to write plus u. And if you remember, the first equation was v equals at plus u. So since v equals at plus u, I can replace this at plus u with v, so s equals half t bracket v plus u, right? Because this at plus u is replaced with v. So now that I've proven the third equation is now proven, let's prove the fourth one, which is just another rearrangement. So let's try and rearrange the first equation. Okay, we got v equals at plus u. Now if we square both sides, we will get v squared equals at plus u squared. Right, and if we try to square it using some basic binomial expansion, we will get v squared equals at plus u times at plus u, and then we will get at times at is a squared t squared, at times u is atu, u times at is again atu, and u times u is u squared, so this becomes a squared t squared plus 2 atu plus u squared. Right, so from this to this, all we have done is we've squared both sides, which means this equation is still equal. Right, the left hand side is still equal to the right hand side. Okay, the next thing we're going to do is we're going to try and isolate the u squared. So I have v squared equals u squared plus, and now what I'm going to do is I'm going to look at these two terms. Now I'm going to take out the common factors of common factor a. So I'm going to take out a, and then what I have left is a t squared plus what do I have, 2 tu, right? So I factorized the a out and put it in front, and now what I'm going to do is I'm going to take the 2 out as well. Alright, so I'm going to take the 2 out, and then I have half at squared plus tu. Yep, so 2a times tu is equal to 2atu still, which is correct. And 2a times half at squared is still equal to a squared t squared. So that's what we want. Okay, now, if you guys remember our equation for s, displacement, right, over here we've said s is equal to half at squared plus ut, and that is exactly the same as what's in the brackets here. So therefore I can change it to v squared equals u squared plus 2as. So now that I do that, I have proven the fourth equation. V squared equals u squared plus 2as. Done. Okay, thanks for watching.